Hello everyone. I would like to continue section 15.4, the second part. Okay, application of double integrals. The second part, just like the first part, basically, we're going to talk about a couple of formulas. Okay, I'm not going to derive the formulas because those are directly from application, say from physics and from statistics and probability statistics. Okay, so we're going to just talk about formula and then we talk about one example. Okay, and the homework, just apply the formula how to do the problems. Okay, let's get it started. Okay, so of course math 1D. Now this is a lecture 18. Lecture number 18. Okay, so we're still in section 15.4. So this is the applications of double integral. Applications of a double integral. So this is a part 2. So we say third application, and this is from physics. We say moment of inertia. Okay, moment of inertia, sometimes we call it the second moment. Okay, and then, in physics, we say this is a quantity expression, a quantity expressing a body's tendency to resist angular acceleration. Okay, I'm not going to talk about from a physical part how do we come up with a definition. We're going to just directly talk about definition. Well, first of all, we start from one point and we say the moment of inertia of a particle. Of a particle of mass m about an axis is defined to be, okay, we say m r squared. So this axis just a straight line, okay, straight line of any direction. So for example, suppose this straight line is the axis, okay, and then suppose there's a particle here, okay, particle with a mass equal to m. And the distance to this axis is r. So this is a right angle, this is r. So we say the moment of inertia is defined to be this, okay? Now, then we say, suppose we say a nominal with density, okay, rho xy, of course, density at one point. So this is the mass unit per area unit, okay? So we say, well, suppose there's a lamina like this. So we say this is in a two-dimensional space. Of course, this lamina can be any kind of shape. Suppose we say this is a D. And any point here inside of this x or y. So we have the density function. And then we say, then we can define the moment of inertia about the x-axis. The x-axis, let me see this axis already better. Okay, is defined to be this. Then we say we use I sub x is equal to the double integral over d of y squared rho xy dA. Now this, your book has the, it's kind of brief of the derivation. So you do partition and approximation. Now partition, you break this the lamina into small pieces using the rectangular pieces, and then on each piece you pick a point, and you pick a point, and then you have a density. Now density, say for example, this is a density, okay, at a point x, y. So this is a density. And then this is the area. So this is the mass. Okay, now you see for this small piece, the mass times the distance, because this is a distance to x-axis. Okay, distance to x-axis, that is a y. Okay, that is a y. And then we say, well, if you think of a small piece, okay, so for example, here you have a small patch, okay, and then density times area is the mass, and then mass times the distance squared. That's the moment inertia of that small piece about x-axis. Now, if you add all the pieces up and then take a limit, that the size of the small piece the patch goes to 0, and then if the limit exists, that's the double integral. So based on the definition of definite integral, we have this. Well, you can look at the book has the limit of a Riemann sum, okay? But here we just directly give you the definition. Now you see the definition basically is a double integral, and the integrand is y squared times the density function. So in the application, you have to give a density function, and then you multiply y squared. So you do the double integral over d, depends on how you describe d, like a type 1 region, type 2 region, etc. So you integrate, you find a moment of inertia. Okay, I think that from math point of view, we just talk about it. This is an application of double integral. If we, from application point of view, this is in physics. So you need to have a more physical background to understand the meaning. And at this point, we just focus on the math part, okay? And then we say the second one is the moment of inertia about the y-axis. Okay, so we say this is I sub y is equal to the integral over d of x squared rho xy dA. Okay, now x squared, you see here, that's x is the distance to the y-axis. So this is the x. Okay, so density times x squared. Okay, density times the area dA, and then that's the mass, and times the x squared, that's the moment of that small piece or of that mass about the y-axis. Okay, and then you add them up. Okay, and then take a limit or double limit, double sum, double limit, and then we have this double integral. And then thirdly, we have this so-called the moment of inertia. Moment of inertia about the origin. Oh, I think the GI. Origin. And then we call this a polar moment of inertia. Polar moment of inertia. Oh. Why I keep writing L there? Okay. Okay. Inertia. Okay. So this we use I sub O. So that's equal to this. Okay. Well, it's understandable. X squared plus y squared is the square of the distance of a point x, y to the origin, right? Okay, so rho is the density, d is the area. That's rho times d is the mass. And then x squared plus y squared, if we take a square root, that's the distance from the point to the origin. Now you square it, that's just x squared plus y squared. But this one, if you break it up to, that's exactly I sub x plus I sub y. So once you find I sub x, I sub y, you find you add them up, that's a moment of inertia about the origin. Okay, so this is we have if they say, for example, d is the region D is given, the density is given, so we can find those three: moment of inertia about the x-axis, moment of inertia about the y-axis, moment of inertia about the origin. Okay, well, your textbook has an example, and then I think I assigned one problem, just applying those formulas. So this one, I'll let you read the example. Okay, now let's move to the next application, is probability. Okay, probability. Now probability, we talk about a function, one variable before. Okay, so here, for example, let's review a little bit. Say here we say probability density function. Okay, probability density function. Okay, probability density function of one variable, okay, y equal to fx. So suppose we have a random variable x, it has a probability density function f. Well, probability density functions, sometimes we just call it PDF. Okay, so here, let me put it here is a PDF. Well, for one variable, it's like this. Now, this function must satisfy two conditions. One is the fx must be non-negative. And secondly, this function integral on, so we say from negative infinity to positive infinity, fx must equal to 1. Must equal to 1. Then we say the probability of a random variable between a and b, x between a and b, is equal to this from a to b fx dx. That's a function of one variable. So this is the left hand side we call it the probability probability for the random variable x be between a and b. Okay, that means the value of a random variable of x is between a and b. So this is when we deal with the function one variable. Now we have say here in xy, okay, instead of R2. So first of all, we say PDF, probability density function, okay. So we're going to have this, first of all, this function, two variables, again, must be non-negative. And this integral over R2 of fxy dA must equal to 1. So satisfy those two conditions. Now you see, the left-hand side is what? Is from negative infinity to positive infinity, and from negative infinity to positive infinity, fxy dx dy. Well, sounds like a, we're going to deal with like an improper integral, because the limit is the lower limit, upper limit are infinity. But most of the time, depends on the function defined. The function only in certain region, the function is positive. Outside the region, it's all 0. Okay, so we can just integrate in the region. We're going to see example. Now, when we have this PDF, then we say we have this formula. We say this probability for random variable. We use x, y, okay, capital X, capital Y, inside of this planar region D is equal to this double integral of fxy dA over D. So that's the probability for the random variable xy. Okay, you form a pair of random variables. Okay, each value is a point in the planar region. Okay, now let's look at one example. Okay, here. Okay, let's follow the first part. So this is example 3. First part, we talk about two examples. We say, suppose the joint, we call it joint joint PDF of random variables x and y. Well, we use capital X, capital Y denoting random variable, and then we use a lowercase x, y representing the value of the random variable. So here we say is this P df is fxy, so the lowercase xy is the value of the random variable. So it's given to be this way. We say a constant c times x times 1 plus x if, say here, x, we say x is between 0 and 1, and y is between 0 and 2, and otherwise is equal to 0. So you can see this function is defined on the R2, on the whole plane, but only on the rectangle from 0 to 1 for x, y from 0 to 2. Only on this rectangle is not 0. Outside of this rectangle is completely 0. So we ask you to do three things. Part A, what is the c equal to? Find what is c equal to. Well, you said it's a PDF. So PDF must satisfy two conditions. Okay, first of all, is the non-negative. Second, the integration equal to 1 over R2. So we're going to use the second condition. Well, if the first condition is non-negative, that means C has to be non-negative. And then we need to find the value anyway. So part B, we say, what is it? We say find this probability for x, this random variable x less than or equal to 1, and variable y less than or equal to 1. Okay? And then part C, we say find, how about we say probability for x plus y less than or equal to 1. Okay? So we need to do those three things. So here, let's see. Solution. Okay. Now, the integration, earlier we say is this R2 and f x y dA. So this is part A. Must equal to 1, right? So this is, say, y change from 0 to 2, x change from 0 to 1. Okay, because if it's a rectangle, the order doesn't matter. You can put it x first and then y. You have the same. And then we say, well, you see, why not from the infinity, negative infinity to positive infinity? Because from negative infinity to 0, from 2 to positive infinity, those two parts, the functions are 0. So that means that we can directly write this. So here, this is a c, and then x, 1 plus x. On this rectangle, it is the piecewise defined function is like this. So this must equal to 1. On the outside of this rectangular box, it's equal to 0. Okay, so now of course this c is a constant. C move out, and then well this one integral with respect to x has nothing to do with the y because of variable y is not involved. So that means you move this whole thing out. You have 0 to 2 dy, which is a 2, and then this the antiderivative, say x plus x squared is half x squared plus 1/3 x to the third, and then plug in 1, 0. Okay, so this is equal to 1. Now, 1/2 plus 1/3 is 5/6. So that means you're going to have a 5/3 C equal to 1, which means C equal to 3/5. Okay, so that's C value. And then part B, well, probability of X less than equal to 1, Y less than equal to 1. So this is just equal to, okay, well, X less than equal to 1, that means X from negative infinity to 1. But from negative infinity to 0, function equal to 0. So we only need to say from 0 to 1. That's the X value. Well, you can do X value first. And then Y value is from negative infinity to 1. Again, from negative infinity to 0 is equal to 0. So it's 0 to 1. And then C is 3/5. We can just use the C. And then here's the X. 1 plus X is a dy, dx, or dx, dy, both from 0 to 1. Okay, so this is equal to 3/5. Okay, so, well, if you want 0 to 1, and then here when we integrate, so this is again 1/2 x squared plus 1/3 x cubed, and then plug in 1, 0 dx. Now this is a constant 5/3. 5/6, sorry, 5/6 move out, and then that's equal to 1/2, right? And then integral, so the constant 1, okay, so that's, let me see, I think, okay. I think the first, let me see, the first integration, yeah, I think I probably should do something like this. Okay, notice this multiply, and then here is 0 to 1 dy. Because this part with respect to y is like a constant, can move out. And then 0 to 1 dy is 1. Okay, so that's just equal. Yeah, this part is the equal to 1. And yeah, I think that's so here you're gonna have a 5/6 times 3/5, so that's equal to 1/2. Okay, the third part C, we ask you to find the probability of X plus Y less than equal to 1. Now, if you look at this, maybe we draw a picture is better. Okay, so this is suppose this is a X, this is a Y. Okay, the random variable. Okay, we can use a capital X, capital Y. Okay. Now, x plus 1, x plus y equal to 1 is this straight line, right? Straight line, okay? And then we said this is a x plus y equal to 1, okay? Now, this one, so we, if you think about this is the region, so this is equal to D, okay? And then if you look at it, 3/5 x 1 plus x dA, that's like this. Well, you say, how to know? Well, you see, this is from 0 to 1, and this is from 0 to 1. Okay, that's completely inside the rectangle from 0 to 1, 0 to 2. So here is from 0 to 1, from 0 to 2. That's a rectangle. Okay, x change from 0 to 1, y change from 0 to 2. This triangle is completely inside that. Inside that, of course, we use this integrand. Okay, use this integrand, outside is a 0. So we need to describe this, whoops, I need to, okay, we need to describe this region. We need to describe this region. So this region, you can describe x first or describe y first. So if you describe y first, say for example, so that means the y change from 0 to 1. Now x change from, if y change from 0 to 1, you give a y value, x change from here to here. So x change from 0 to 1 minus y. And then here is a 3/5. X 1 plus x, and then dx dy, remember, dx dy. Okay, now, so this is equal to integral from 0 to 1. You integrate with respect to x, of course, 3/5 is constant. And then you have a 1/2 x squared plus 1/3 x cubed. And then plug in 1 minus y, 0, dy. Okay, so here we are going to have a 3/5 move out. And then integral from 0 to 1, 1/2 1 minus y squared plus 1/3 1 minus y to the third dy. Okay, well, you break it into two integrals, each one use a substitution. Okay, u equal to 1 minus y. So this is equal to 1/2 and then negative 1/3 and then 1 minus y to third. If you calculate derivative, this 3 come cancel this one. So 1 minus y to 2 times the derivative of 1 minus y with respect to y equal to negative 1. Let's cancel this negative sign. And then plus 1/3 times negative 1/4. And then 1 minus y to the 4th. Now, here we say plug in 1, 0. Yeah, I think usually when we have a bracket, we don't have to put a vertical bar. Okay, so this is 3/5. And then when you plug in 1, that's 0. Minus, when you plug in 0, okay, so 1. So it's a minus, so here's a plus 1/6. And then this plug in 1 is 0, plug in 0 is a 1, so plus 1/12. Right? Okay. 1/6 plus 1/12 equal to 3/12 equal 1/4. So this is equal to 3/20. So let's make this. Okay. So this is this example. And then the last application, okay, fifth part, is the expected values. Expected values. Okay, now this is directly from, say, function of one variable. We talk about expected value, function of one variable. Of course, here when we talk about expected value, that's the mean of the random variable. So we say here, suppose x, y are two random variable. Two random variables. And then we say f x, y is the joint density function. I think I just write joint PDF, probability density function. Okay. Then we have this, we say x mean or expected value for x, random variable x, is defined to be mu1. That's equal to, well, this whole region R2. x times f x y dA. And then we say y mean, okay, or mean of y. That's another term for expected value. Is defined to be mu2. Is defined to be this double integral. And y fx y dA. Now, it really depends on the definition of a density function. A lot of times, the definition of density function, the density function is non-zero in the finite region. Outside the finite region, it's equal to 0. Okay, so you can change the integration over a finite planar region. Okay, so here again, I'll let you read the example in the book. You see, this is just an application of a double integral. Okay, yeah, please read the book and then practice couple problem, finish the homework. You should be able to understand it. Yeah, this section, basically we just list a couple examples, okay, and then the application, just apply those formulas to do calculations. That's an application of double integral. Okay, so we talk about 5 applications. Okay, so please read this section carefully and then do the homework problem. Okay, I'll talk to you next time. Okay, bye-bye.